Okay, so now let's take closer look at how compound interest connects exponential functions. So if a set of data has an initial value a and a constant percent change r, then the data can be modeled using exponential function y equals a times 1 plus r to the power x. So this is exactly how compound interest works. So suppose you have invested $1,000 at a rate 6% annual interest rate. So this is compounded once per year. So that means the principal, so let's take the principal A as 1,000 and the rate R is 0.06, then the number of years T is our input. So T is our input. This is the number of years. So the future value of this investment after T years is given by S. So S is equals, the initial value is 1,000 times 1 plus R, which is 0.06 to the power T. So this exponential model shows how your investment grows over time, not just on the initial value 1,000, but also on the interest that keeps building up on each year. Okay, so now let's explore how 1,000 grows at 6% annual interest over time using a table and graph. So let's try to calculate future value for each year from t equals 0 to 5. So let me write the formula first. So S equals, okay, let me take this page. So S equals 1,000 multiplied by 1.06 to the power t. So here I'm trying to calculate the compound interest or future value s for each time from t equals 0 to 5. So let's start with t equals 0. So this is the initial value. So to get the future value or s value at t equals 0, what you have to do is you have to substitute t equals 0. So if you use this formula in your calculator, you'll get $1,000 for the first value. And to get the s value at t equals 1, you have to substitute t equals 1 into this formula. In that case, you'll get $1,060. Okay, to get the third value, you have to substitute 1,000 multiplied by 1.06 to the power 2. That value is going to be approximately 1,123.60. And next, S equals, you have to substitute 3. So that value is around 119102. So you can use your calculator to get these values. So I'm going to give the other two values. It's around 1262.48, and next it's 1338.23. So this table shows the future value for different t values starting from 0 to 5. Okay, so part 2, you have to graph the function. For the given values in part A. So here in this table, let's take our inputs as t values and outputs, we are going to take them as y values. The outputs are going to be future values. So in that case, these are the points that you have to plot. So I'm going to write the points over here. Okay, so let me take a new page. These are the points you have to sketch. The x value is 0 and the corresponding y value is going to be 1,000. This is your first point. And the second point is this. Third point is this. So likewise, you will have 3 other points. So you have to take these points and you have to sketch a scatter plot. So this is the scatter plot for the given data in this table. Okay, let's move to the third part. So in the third part, you have to graph the function as a continuous function. So this is you have to sketch this as a continuous function. So instead of whole numbers, you have to graph the function s comma t 1000 multiplied by 1.06 to the power t. So for the values t from 0 to 5, which means for continuous function, it include decimals like zero point 0.5, 1.3. So likewise, it includes all the decimals value. So what you can do is you can sketch this graph for the t values from 0 to 5. So then you'll get a graph like this. So this continuous curves gives more complete picture of how the investments grow at any moment during the 5 years, not just at the end of each year. Okay, so the third part, it asks, is there another graph that is more accurately represents the amount that would be in the account at any time during the first year that the money is invested? Okay, so let's go back to the second part. So here in the second part, you can find the scatter plot we sketch for the given set of data. So this shows the amount in the account at the end of each year, but not at any other time during the 5 year period. And moving on, next we have the continuous function. So this continuous graph shows the amount continuously increases, but the interest is paid only at the end of the year. So the amount in the account is constant at the previous level. So actually this scenario is well illustrated in this graph. So this is more accurate graph of the amount that would be in the account, because it shows that the amount remaining is constant until the end of the year where the interest is added. Okay, so now let's talk about future value of an investment with annual compounding. So when you have an amount in P dollars is invested and an annual interest rate R, the compounded once per year, then the future value S of an investment after T years is given by this formula. So we have seen this formula. So here S represents the future value of the investment, and P represents the principal value, and R represents the annual interest rate. So this is usually a decimal, and T represents the time in years. So this formula reflects exponential growth. So we just discussed an example with this formula. So your investment grows not just on original amount, but also on the interest it earns years after year. So this formula reflects exponential growth. So your investment grows not just on the original amount, but also on the interest it earns years after year. So you can use this formula when the interest is compounded annually. So that is added to the account once per year. Okay, so now let's talk about future value of an investment with periodic compound. So over here we talk about how the compound interesting work annually. But what if the interest is compounded more than once per year? So then the formula for the future value of an investment becomes this. So here S represents the future value of an investment, and P represents the principal, which means the initial value, and here R represents the annual interest. Usually this is a decimal value, and over here K represents the number of times the interest is compounded per year, and T represents the number of years. So here in this formula, R over K represents the interest rate per compounding period, and K times T represents the total number of compounding periods. And this whole expression shows how money grows as interest is added to multiple times per year. So this model is specially useful for investment that is compounded quarterly. Let me write that. So that means K is equals to 4. If you're trying to calculate the compounded interest monthly, you can use this. In that case, your K is going to be 12. And if you're trying to get the interest daily, in that case, your K is going to be 365, or you can use any other frequency. So the more frequency interest is compounded, the faster the investment grows. So let's try an example. Okay, so here you have to find the future value of $10,000 invested at 8% annual interest for 10 years. And the compound, what if the future value, if it is compounded annually, and next you have to calculate the daily compounded values. And finally, you have to find how much is more earned by compounding daily. So let's start doing this problem. Okay, so first part you have to get for annual compounded interest. Okay, so first of all you have to identify your principal value is $10,000 and your R is equals to 0.08 and K, here we are talking about annual compounding, so K is equals to 1. And the T is, we're talking about 10 years, so T is equals to 10. So your formula becomes S equals principal value, which is $10,000 to the, you have to multiply it by 1 plus R over K, which means 0.08 divided by 1 to the power K times T. So K is 1 and T is equals to 10. So if you multiply both together, you get a 10. So this is the formula. So if you use your calculator, you can get the value 21,589.25. So thus the future value is this much. Moving on, let's move to the second part. So the second part, you have to calculate the compound amount if you do this daily. So in that case, the P stays same, R also stays same, but K now becomes 365 because we are trying to get the interest compounded daily, and the T also 10. So now you have to put this value into your formula. So P is 10,000, 1 plus 0.08 multiplied by 365. And if you multiply K by 10, you get 365 times 10, you'll get a 0 over here. So if you use your calculator to evaluate this value, it becomes 22,253.46. So now you have to get the difference to find out how much more is earned by compounding daily. So that means you have to get the difference. So if you subtract the values for C, you have to divide, you have to subtract this much and 21,589.25, which is around $664.21. So that means daily compounding gives 664.21 more than the annual compounding. Okay, so now let's talk about future value of an investment with continuous compounding. So when interest is compounded continuously, we use a special exponential formula that gives the that involves the number e, which is approximately 2.71828. So the formula for the future value is S equals P times e to the power RT. So here S represents the future value of the investment and P represents the principal or initial value, and R represents the annual interest, which is going to be a decimal, and T represents the time in years. So here E is the Euler's number, a mathematical constant used in exponential growth. So this formula shows the maximum possible growth for a fixed interest rate. So this is what happens when the interest is being added infinitely often in time. Okay, so let's try an example. So here you have to calculate the future value with continuous compounding. So in this problem, P is going to be this value, which is $2,650. So this is your principal value. And interest rate R is going to be 12%, which is going to be 0.12, and the time t is 8 years. So now you are going to use the formula S equals P to the power ERT to get the future value at the end of 8 years. So what you have to do is you have to use this formula. The principal is $2,650. E to the power R is 8 times 0.12. So if you use your calculator, you can have the value of $69,2100. So this is the future value of this investment. Moving on to the next part. So how much interest will be earned on this investment, which means you have to you have to take the difference between these two values in order to calculate the interest earned on this calculation. So you have to take the difference. So that means you have to subtract 2650 by 6921. So let me subtract the principal value, which is this. So then you'll get around $42.71. So this is the interest that earned by this investment.